How familiar are you with support vector machines, SVM, and linear discriminant analysis, LDA? Whether you're a data scientist, a machine learning enthusiast, or simply curious, these are two concepts that you're bound to encounter in the field of data analysis and prediction. In a nutshell, support vector machines, or SVM, is a supervised learning model with associated learning algorithms that analyze data and recognize patterns used for classification and regression analysis. On the other hand, linear discriminant analysis, or LDA, is a method used in statistics, pattern recognition, and machine learning to find a linear combination of features that characterizes or separates two or more classes of objects or events. Now, these might seem like complex concepts, but don't worry. Over the next few minutes, we're going to break them down, explore them in depth, and help you understand their distinct characteristics and applications. Let's start with SVM, a very versatile method that makes no assumptions about the data. Support vector machines, or SVMs, are a type of supervised learning model that can be used for both classification and regression tasks, but they are particularly well known for their applications in classification problems. SVMs work by trying to find the optimal separating hyperplane, a boundary that separates different classes of data. They aim to maximize the margin, which is the distance between this boundary and the nearest data points from each class. These nearest points are known as support vectors because they support or define the decision boundary. Now you might be wondering, what if the data isn't linearly separable? That's where SVMs show their flexibility. They introduce a slack variable to allow for some overlap between the groups. This means that even if the data isn't perfectly separable, SVMs can still find a decision boundary that does a pretty good job. But wait, there's more. SVMs can also handle nonlinear classification problems. How do they do this? By using something called the kernel trick. This is a clever mathematical technique that transforms the data into a higher dimensional space where it becomes linearly separable. So even if your data looks intertwined and messy in its original form, SVMs can map it to a higher dimension and find a separating hyperplane there. However, SVMs do have their limitations. They are primarily binary classifiers, which means they work best when you have two classes. If you have more than two classes, you will need to use a strategy like one versus all or one versus one, which can be computationally expensive. In conclusion, SVM's strength lies in its ability to handle complex, high-dimensional data with a certain amount of overlap between classes. However, it may struggle with more than two classes, yet its flexibility and ability to deal with nonlinear problems make it a valuable tool in the machine learning toolbox. Now, let's turn to LDA, a method that makes specific assumptions about your data. Linear discriminant analysis, or LDA, is a classification technique that assumes your data is normally distributed. This means that it presumes your data points will fall into a bell-shaped curve or normal distribution. This is a crucial assumption that sets the stage for how LDA operates. LDA also assumes that all groups in your data are identically distributed. If the groups have different covariance matrices, LDA transitions into a different technique known as quadratic discriminant analysis. It's important to note that these assumptions don't limit LDA's power. In fact, if all assumptions are met, LDA is considered one of the best discriminators available. Perhaps one of the most distinctive features of LDA is its use of the entire dataset to estimate covariance matrices. Covariance matrices measure how much two random variables fluctuate together. By using all data points, LDA can gauge the overall spread and orientation of the data in multiple dimensions. However, this approach also makes LDA somewhat prone to outliers, which are extreme values that can skew the analysis. When it comes to handling multiple classes, LDA shines. It can manage several classes effectively as long as its assumptions are met. This makes it a reliable choice for multi-class problems. Further, LDA can be a valuable tool for feature selection when the number of predictors is greater than the number of observations. Feature selection is a crucial step in machine learning, helping to identify the most relevant input variables for predicting the output. By using LDA, you can select features that maximize the distance between means of the groups, enhancing the model's predictive accuracy. In summary, LDA is a method that, while less flexible than SVM, can be a powerful tool when its assumptions are met. It's often a go-to method in initial analysis, providing a solid foundation for understanding your data and making informed predictions. Having understood SVM and LDA separately, it's time to put them side by side. Here's a snapshot of their differences. SVM is like a flexible gymnast. It doesn't make any assumptions about your data. LDA, on the other hand, assumes your data is normally distributed. It's like a meticulous statistician, making precise calculations based on specific assumptions. In terms of flexibility, SVM can bend and twist to fit your data. It's optimized over a subset of the data, the points that lie on the separating margin. These points are called support vectors, as they support the classification. LDA, however, uses the entire dataset to estimate covariance matrices, making it somewhat sensitive to outliers. When it comes to classes, LDA handles several classes well, as long as the assumptions are met. SVM, though, prefers a one-on-one match and doesn't really discriminate well between more than two classes. Also, if you're dealing with a large number of variables, SVM has an edge. It has dual and primal formulations that allow you to optimize over either the number of data points or the number of variables, depending on which is most computationally feasible. In short, SVM and LDA are like chalk and cheese. SVM is the flexible, adaptable method, while LDA is the more traditional, assumption-based approach. They have very little in common, but they are both tremendously useful tools in data analysis. To wrap up, let's summarize the key differences between SVM and LDA. SVM stands out for its flexibility and optimization over a subset of data, allowing for some overlap between groups. On the other hand, LDA operates under certain assumptions and makes use of the entire dataset, which can make it more susceptible to outliers. While both methods are tremendously useful, the choice between SVM and LDA hinges largely on the specific characteristics of your data and the problem you're aiming to solve.